Sorry, for 1 second, the Wi-Fi went down, so I'm trying to get my computer back connected. What the fuck? Okay, so we're gonna get started here, and if you try to download the slides, there's some issues uploading the correct version. Hopefully the slides on the website are correct now, and not the incorrect draft version. If you have to refresh a couple times, you might have to make sure that the proper slides went in there. I don't know, let me know if the slides look like they have weird errors in them. They should have properly been uploaded, but tried a few times there. Okay, so today we're going to continue with our lectures on support vector machines. We're actually going to do a bit of a recap of some of the stuff we talked about last lecture. Also have some pointers to some textbook material that is useful for this. I know it's a concept that is somewhat requires a bit of offline learning in addition to the lectures. But also, before we get to that, quick update on Mini Project 2. So Mini Project 2, this is the current state of the top of the leaderboard at least. So still there is only 2 groups who are currently beating my benchmark, but there is a whole ton of groups that are right by it. So again, make sure that if you're curious about how your grade is impacted by these things, the formula is in the assignment spec. And I think like this one right here, that's right below mine, I think that's like basically like a 29.99 out of 30 or something on this component. So make sure you're using your time wisely in terms of how you're optimizing on this data set here. And again, looks like a lot of people are getting close to my benchmark, still only 2 people beating it. And even if right now, again, these 3 groups, so not including me, would get the bonus points. So you don't have to beat me to get the bonus points, you just have to be in the top 3. So the other thing that I've mentioned a lot with Mini Project 2 is, again, this point that the competition is only part of your results or part of your grade, and writing a good project report is another big aspect of this. And so a lot of people have been wondering, what does it take to write a good report? And this is challenging. I know that for a lot of machine learning computer science courses, writing isn't maybe a really big component of it. Writing good project reports is usually more of a thing in graduate level courses. This is a graduate level course. It is a 500 level course. So we do have this expectation that you do a good job in this somewhat more open-ended project report writing aspect of things. Since this is the first year where I am teaching this course and where it's being taught in the style that I do it, there is unfortunately no examples I can show you of, look, here is a perfect report from last year. So one thing I will give you as examples is trying to read some good machine learning papers that are out there. And in particular, there are conferences, top conferences, where people publish very good papers where they're short papers, where they're 4 to 5 pages. And so for people who are wondering, like, how much can you do in 4 to 5 pages, you can check out some of these examples. I think maybe even one of those is a paper that I was an author on. So these are things from workshops, from conferences. Again, they're all 4 pages, at least they should be without the appendices. And in general, of course, these papers aren't going to be a project report. They're going to be about some particular machine learning problem or some natural language processing problem. But they're going to give you a good idea of what a good write-up looks like, how to do citations, how to have nice figures, all these kinds of things. So this will be useful in terms of trying to get an understanding of what a good project write-up looks like. And again, something that I'll mention is that, again, in this mini project, everybody's starting to get pretty clustered up here, and people are starting to get high grades. If things were planned correctly, mini project 3 will not be as easy to get all the way up to near the top. So again, this mini project is a difficult task. This is non-trivial, but I'm really trying to hope that people are getting up around here and then really spending more time running experiments, doing some nice, tests of saying, like, which are the hyperparameters that matter, what are the good figures to explain, say how, the accuracy trades off as I, change this hyperparameter, say the number of words I'm including, so how big my vocabulary size is, how does my accuracy impacted by that, how does the accuracy compare against some different types of models, what's a nice table to show that, and these sorts of things. So that's the hope, the expectation, and we will try our best. Of course, there's many of you, even divided by 3, still more than 100, but we'll try as much as we can to give feedback and suggestions for improvement so that when we move from mini project 2 to 3, you actually have some concrete feedback in terms of what you could do better on your reports, or what was really great in your reports and what you should continue to do in the next one. So that's just a quick bit of logistics there. Now we're going to return to support vector machines. So we're going to start off just by recapping a bit of last lecture, because we're going to build specifically on that. So it's important to reiterate this. And the idea here, again, is that we're trying to do classification, focusing on binary classification, using this idea of maximizing a margin. So what we want to do is we want to maximize this margin M, where this margin is the distance from our decision boundary to the nearest training point. And what we're trying to do is we're trying to maximize this margin by optimizing our parameters, and then we have this constraint here, which is basically saying that we want all of our points to be classified on the right side of the margin by that degree. So we're saying make M as big as possible, such that we have the points on either side. And this original problem seemed reasonable, but we had this issue where it was unconstrained, and this meant that practically what's happening here is that W, our parameter vector, is specifying the direction of our decision boundary, but we're kind of free to change the magnitude of W as much as we want. That part is unconstrained, and in particular what this means is that if we have a solution, we can multiply our weights by a constant scalar, and that solution is still a valid solution to this problem. So what that means is that it's not really a nice optimization problem. So what we did was we added a constraint where we said, okay, we're free to set the magnitude, the norm of our weight vector to whatever we want. Well, we're going to presume now, to make our model more constrained, that the size, the magnitude of our weight vector is actually what's determining the size of the margin. So I think the visual way to look at this is that in our original unconstrained formulation, what we had was we were trying to maximize this margin, and we were specifying our decision boundary with this parameter vector, which basically tells us, what is the normal to this decision boundary. And we're trying to maximize this margin by setting this decision boundary, but the size of this arrow, the magnitude of this vector, was just a free thing that wasn't constrained in our model. So the thing that we did to make this actually a well-defined optimization problem was that we set this size, the size of W, to specify the margin. So instead of having this margin and this parameter vector, what we did to have a well-defined optimization problem is we said that the direction of W tells us the orientation of our decision boundary, and the size of W tells us how big the margin is. And now that we've done that, we can then have a revised and well-defined optimization problem where what we're minimizing is we're now minimizing the magnitude of W, because again, the magnitude of W, if it's really big, this is going to have a big margin, so we're trying to minimize this, because we have an inverse relationship between W and M. And we also did this thing where we took the square, and we took the square just to make this optimization better for an off-the-shelf optimization, quadratic programming solver. So you don't need to really worry about why we took the square there, but the important thing is that minimizing W squared is equivalent to maximizing M squared, which is equivalent to maximizing M. So this was this basic idea. We wanted to maximize the margin. We played some tricks, or some necessary tricks in terms of making this a well-defined optimization problem. Then we went over this notion of Lagrangian optimization. And here the key idea was that we had this constrained optimization problem where we had, let's minimize f or maximize f. We have some optimization or some function we're trying to optimize, and then we have some constraints. And what we could do with this Lagrangian multiplier is a style of transforming this constrained optimization problem into, in some sense, a less constrained optimization problem, is with this trick where we say, okay, we're still trying to optimize f here, but now we've turned all of our constraints into something that we're just summing over in the objective. And what this results in is that we end up with an optimization problem where if our constraints are satisfied, we're just optimizing our objective. Otherwise, the objective function is infinity. So at the end of the day, after playing again more of these kind of optimization tricks, which are all very kind of well-motivated things that we do in order to make this optimization tractable, we end up with this idea that we have two versions of our optimization problem. We have what's called the primal. So the primal here, this is where we're trying to minimize our function with respect to our weights after we've done this maximization up here. And again, this max term is going to be infinity if we don't satisfy our constraints. So first off, what we do is in here, we're trying to satisfy our constraints within this max term. And then over top of that, we're doing the minimization. And then we introduce the idea of having the dual of this, where we flip the max and the min. So instead of doing a minimax, we're doing a max-min optimization. And what this results in our case of actually trying to do SVMs, is that we have this particular Lagrangian function. So again, this is the thing that we're trying to minimize, this 1/2 times the norm of W squared. These are our constraints. On the right there, these alpha I times 1 minus y with the product of our decision boundary. And we have two ways of representing this problem. One in the primal sense. So the primal sense is we're saying, first, we're trying to maximize this Lagrangian with respect to our alphas. And this maximization is really just a clever way of trying to satisfy our constraints, because if our constraints are satisfied, then the best we can do is setting all these alpha i's to 0. But if our constraints aren't satisfied, then we can have infinity for this max term. So this max term is just a clever way of turning our constrained optimization into more of an unconstrained optimization. And then we're trying to minimize over W on the outside. And we can flip the max and the min, and we can do this flip from what we call the primal to the dual because of some nice theory surrounding convex optimization. And in particular, if we have that our objective function and all of our constraints are convex, and we have this linearly separable data, there's a number of assumptions we need to make here, but under assumptions that are nicely satisfied for SVMs, the solution to this min-max problem will be the same as the solution to this max-min problem. And this means that instead of solving our original thing at the top there, this constrained optimization problem, instead we can solve this dual optimization problem, this max-min problem down here. It's all going to give us the same answer. And there's some discussion of this in section 7.1 of the Bishop book. There's a detailed discussion in the appendix. You're not going to be responsible for the detailed discussion in the appendix and in kind of other references they make that actually gives proofs behind why all this is true. But what's in section 7.1, which is really just a slightly more detailed version of what's in these slides, you should be familiar with. And at the end of the day, what we're going to solve is this max-min problem. Again, originally what we wanted to do was this constrained optimization. We've turned it into this dual problem of this max-min. We can solve that first by solving the min that's inside. So we have the max and then the min. So we can solve the min of this Lagrangian with respect to the weights by taking derivatives, setting to 0. And then at the end of the day, we can plug back in the solution we get from the min, and then that allows us to transform the W into a function of our data points and our alpha i's. We can plug all this back into another quadratic programming solver. And at the end of the day, what we get is that to solve this SVM constrained optimization problem, we instead solve this dual. And what this dual gives us is it gives us a whole bunch of alpha i's. So one alpha I for each training point. And these alpha i's have this really nice property where these alpha i's are only going to be non-zero for points that are exactly on the margin. And again, we call these points the support vectors. And what's nice about this is now we can actually represent our decision boundary as just a function of our input points. So what we're really learning is we're learning this weight vector. We wanted to find the weight vector that gives us the decision boundary with the best margin. But we'd done a whole bunch of steps of transforming an optimization problem to come at the end of the day to a problem where what we're learning is weights over all of our training points, and where these weights together specify our decision boundary. So at the end of the day, our prediction on a point x is given by this function here. We're summing over all of our training points, taking these alpha i's that we're learning, and multiplying these alpha i's times the class value for that point, so 1 or -1, that's the y value, and then the dot product of the feature for that point and the feature of the point that we're trying to predict for. And again, an important thing to note here is that we're summing over all of our input points, but most of these points are going to have alpha I equals 0, right? So really we don't need to actually do this sum over 1 to n. We really need to only sum over the non-zero alpha i's. And I want to point out that it is possible to just solve this original constrained optimization problem shown here at the top. And we went through this transformations of this, first using this idea of the Lagrangian, where we did this trick where instead of having these constraints, these such-that constraints, we just folded these into this maximization term. And then we did this flip where we flipped the max and the min, and we were allowed to do that because of the theory of convex optimization. And we did all of this really so that we could come to this version of the solution where our decision boundary is specified as a linear combination of our input points. And that's going to be really important. So again, if you're doing just a plain linear SVM, you can just put this original constrained optimization problem into a solver. You don't need to worry about the Lagrangian and the primal and the dual. But it's going to be very, very useful as we come to more complicated versions of SVMs to have this version of the solution that is in terms of the training points. I just want to make that clear in terms of all of these Lagrangians and the primal and the dual isn't necessary to get the solution for linear SVM, but it's important because for some more complicated versions of SVMs, working with this dual representation of the classifier, where again, the dual representation, we're representing the decision boundary as just some linear combination of the input points, that's going to become very, very useful. And I know, and I said it in the last lecture, and it's a bit of a broken record on this, but this is tricky material to follow in a lecture format because it's just a bunch of transformations of some optimization objectives and a bunch of references to optimization material that you may or may not have seen in the past. because it's not a prerequisite to know the optimization material for convex optimization and what Lagrange multipliers are, and things like the KKT conditions, which are mentioned at one point in one of the slides. So what I'm going to say here, just to make it really explicit in terms of A, what I recommend, and A, what I expect, is the content in these lectures really closely follows, in this case, one particular textbook, which is the Bishop textbook, and pages about 325 to 343. This is one of the textbooks that's freely available. So I'm going to say that I recommend reviewing that because it's basically what's in these lecture slides with a little bit more words explaining things. It also goes through a bit more detail in terms of dealing with the bias term, actually showing exactly how all of these things play out. So you don't need to know things from the appendix, but you should know 325 to 343, which is basically what's been in these slides. And that's the place where I'm going to give, in this case, a firm recommendation in terms of this is the textbook we should look at for this SVM material. The other textbooks do have material on SVMs, but in some cases it's more advanced than you need to know. So what's in a sense, Chapter 7, especially Section 7.1, is the level of SVMs you should be familiar with. Any questions at this point? Yeah. Yeah. This is a great question. So here we've been talking about binary SVMs, and again we have this single decision boundary. So what do we deal with? How do we deal with the multi-class case? I'll actually have a couple slides from that towards the end of this lecture. So we will cover that. And again, I think there's probably a more concerning issue that came up a couple times in last lecture, and also with questions at the end of last lecture in terms of what does and doesn't make sense in terms of this version of SVMs that I've been describing. Well, the first thing to note is that this entire time we're totally acting under the assumption that our data is linearly separable, right? If we go back to our constrained optimization problem here, we're trying to find the best margin so that we can classify all of our data points where they're all at least that margin away from the decision boundary, right? But we can't satisfy all these constraints if our data is not linearly separable. So I said you can just throw this into a constrained optimization solver, but it's really only going to actually give you an answer if your data is truly linearly separable. And this also raises another point that somebody raised where they said, well, isn't it crazy to say that we have all these support vectors that are lying right on the margin? Like, what are the odds of that? Of all these points being exactly, 5 points all being exactly margin distance away from the decision boundary. That seems kind of improbable. Well, it is somewhat improbable, but also having linearly separable data is also somewhat improbable. So far up until this point, this has been a reasonable, almost conceptual exercise in how we could build a perfect classifier that would maximize, that would come up with a really sensible decision boundary, presuming our data is almost perfect and can be separated. So now, for today, we're actually going to talk about real data, and real data will almost never be linearly separable. There's going to be noise in your data, there's going to be more complicated types of decision boundaries, etc. So what are the things that we do to actually deal with SVMs and deal with these kinds of decision boundaries in the real world? Well, there's really two options, and we call them option 1 and option 2, but these aren't exclusive. You want to do both of these things, and we'll cover both of them in this lecture. So the first thing that we want to do is we want to actually relax this optimization a little bit, where we're not going to say every point has to be on its side of the margin, or its side of the decision boundary by the margin. We're going to have some tolerance for misclassification. So we're going to relax things a little bit. The other thing we're going to do is we're going to accommodate nonlinear decision boundaries. So these are the two things we're going to play with. On one side, we're going to go from what we call a hard SVM, where this hard SVM is saying, let's perfectly linearly separate this data with a very sensible decision plane that maximizes the margin. Now we're going to say, okay, well, first off, some things might be on the other side because the real world has noise. And the second thing we're going to do is we're going to say, okay, many real-world data sets don't have a linear separation. They're probably better with some sort of nonlinear decision boundary. So beginning with this idea of softening the decision boundary. So the original thing that we were solving was this constrained optimization problem. Again, we're trying to minimize the norm of W subject to this constraint, basically saying we're classifying everything correctly. So again, the way to interpret this constraint up here is we're saying that if Wt times x is greater than 1, well then we're classifying this point as a 1, and so the product with that and 1 should be positive. If Wt times x is negative, then we're classifying that point as negative, and then the product of that negative classification with the fact that this is actually a negative example would again be positive. So we're saying that we're making the right classification choices, and not just making the right classification choices, but doing so with this margin, where our margin here is just 1 because of the fact that the actual size of the margin is being specified by the norm of W. So this was the original thing we were trying to solve. And we can actually rewrite this thing. Again, we're going to start rewriting this optimization equation in different ways. And we're going to rewrite this now as, again, a minimization. But now we're going to have a minimization over a loss function. So our loss function in this case is going to be a loss function where we're comparing our prediction, again, Wt times x, that's our prediction, and what the true value is for this training example. So now we've introduced this kind of a bit more familiar where we're saying, okay, we're trying to minimize over some loss function as well as over the norm of our weight vector. And in fact, this looks a lot like L2 regularized regression. If this was our classic loss function for regression, this would actually be what it looked like for doing L2 regularized linear regression. That's not what we're doing here, but there's close relationships. But again, all this is doing is this is just saying, let's try to minimize our error as well as the norm of our weight vector, but we're still going to have these constraints. And our loss function here is kind of crazy. Our loss function here is basically saying we have infinity if we make any mistake. Any training example that we're wrong on, this makes us have an infinite loss. And then we just have 0 loss when we do things correctly. So basically, adding this extra loss function on the top in terms of our objective, what we're trying to minimize, didn't change anything at all, because this is again just saying you either have to be perfect and classify everything correctly, or you don't get a solution. You have an infinite thing. You can't minimize something if we're setting it to infinity. So we didn't actually change anything here. We just said, well, we can think about there being this really, really harsh loss function that's giving us an infinite loss anytime we make a single mistake. So how might we want to actually soften this and say, okay, we have some tolerance for making mistakes? Well, we can do that by changing this 0 to infinity loss function as 0 to something non-infinite. And in fact, again, we'll just make it 0, 1, because we can trade off how much we care about the classification by, say, adding some weight on top of this loss. So basically going from this idea of you get 0 loss when you're correct to infinite loss when you're wrong, now we're saying you get 0 loss when you're correct and you get a loss of 1 unit when you make the wrong choice. And now we have a slightly more sensible, softer objective, but the problem here is that this 0, 1 loss is again something that's very non-convex. It's not a very nice function. It's not differentiable. If we're looking at a step function, it's a very gross function. You can't take the nice derivative of it. It's not smooth. It's non-convex. And so this again breaks our constrained optimization solver. So that doesn't work. And again, visually showing what's going on here, again, using this 0, 1 loss is like having a step function. And generally, everything in machine learning, almost always we want the functions we're optimizing to be smooth, to be differentiable, and ideally to be convex, although that very rarely happens. So the question is, how can we have something that is kind of like a step function, but that is a bit more well-behaved? And the thing that we can use is actually something called the hinge loss. So the hinge loss is this function where what we're saying is that it's basically going to be 0 if we're making the right decision, but then once we start making the wrong decision, it increases. It's a linear function that's increasing in some sense with how wrong we are. And again, this function actually has a discontinuity, but this function is actually nice to work with and is subdifferentiable. So it's, unlike the step function, it's still a little bit rough because it has a discontinuity, but for the most part, it actually plays quite nice with our optimization tools. So now what we can come up with for our kind of smoother, softer version of an SVM is now what we want to do is we want to minimize this hinge loss. So this hinge loss is saying, okay, you're great if you're classifying the point correctly. If you're putting this point on the wrong side of the decision boundary, you're paying a loss. There's a cost that is proportional to how much on the wrong side of the decision boundary this point is. And then we have this C function here, which basically trades off between how much we're willing to tolerate misclassifications versus how much we care about maximizing our margin. So again, if C here was 0, we would go back to just maximizing our margin. If C here is really large, this hinge loss term is going to dominate our optimization. And the important thing here is this hinge loss upper bounds this 0, 1 loss. So it's a sensible replacement for this 0, 1 loss. And what we're going to do at the end is now we're going to again still have our decision boundary and our margin, but now we're going to have some points that are on the wrong side of that margin, and we're paying some penalties, these zeta penalties for these points. And the penalty that we pay is proportional to how much on the wrong side they are. Yep. This is a great question. There's a slight difference between those two scenarios, and we'll actually kind of show the exact, it's generally, it's going to be on the wrong side of the boundary. But things that are within the margin, you also kind of have to pay a bit of a cost for. It's a great point. Okay, so now the way that we're going to write this down in terms of, again, an optimization problem is we're going to define what are called some slack variables. So now these slack variables are actually just the output of our hinge loss. So our slack variable here, this zeta, is going to be how much it's 0. We pay no penalty. There's no slack term for something we classify correctly. But if we're incorrect, we have this penalty that we're paying. And now what we're going to do is we're going to now have a new optimization problem where we want to find the minimum of this objective, where now we're saying we want to minimize the sum of these slack terms. We want to have the lowest loss on this hinge loss term as possible. We also want to maximize the size of our margin. So how this actually transforms is now we're going to have, again, our decision boundary. But what we're saying is that, okay, points have to be on the right side of the decision boundary, but we can have this slack, this kind of penalty that we're paying here. Because if we're really wrong for this point, well then we can kind of, okay, give up on that a little bit. But we don't want to do that too much, and so we're trying to minimize these terms. So we're saying previously we didn't have this minus term here. We're just saying they have to be correct and on the wrong side of the, on the right side of the margin. But now we have this nice little slack that we give our model. And these slack variables are just real valued numbers, and we constrain them to be greater than 0. And you can see that that is kind of by definition. Again, if we're classifying things correctly, well, then we have 0 for these, and these things are on the right side of the margin, so there's no need to have them be less than 0. But if things are really bad, we've really misclassified this point, we might have a huge slack. So this term is 100 units away on the wrong side of the margin. Well, we can accommodate that by having the zeta I equal to 100. Again, we're going to pay a big penalty on that. Our model doesn't want to make these, it wants to make these terms as small as possible, but we're willing to accommodate some error. Now, just like before, we can think about this from, on one side, this constrained optimization problem, or this idea of setting up this Lagrangian, where we're turning these constraints into something that we're just maximizing over. So before, we had these alpha i's, so one alpha I for each of these constraints. But now we have two different types of constraints. We actually have these alpha i's, which correspond to this constraint term, and then these beta i's, which correspond to this constraint term down here. And I'm going to go through this pretty fast, partially because it's a lot of mathematical manipulation, which is not that exciting to hear in person. But what's happening here is just like we did before, where first we had this primal, where now we call the Lagrangian. Our objective function, the thing we're optimizing, is trying to minimize this w, the norm of w squared. We're also trying to minimize the sum over these slack variables. Again, these slack variables tell us how much are we on the wrong side, how much are we misclassifying over all of our points. Trying to minimize this, trying to minimize this, which maximizes our margin. And now we have this term over here, which this is taking these two constraints and instead writing these constraints as just terms that we're multiplying by alpha I and beta I. And just like before, we can take the min and then the max of this function instead of doing this constrained optimization. We can take this max min, we can do this dual idea with inverting that to the min max. We can solve this dual by doing some differentiation and finding where the gradients or the derivatives equal to 0. We can plug everything in, and at the very end of the day, we get a very, very, very analogous thing to what we got when we did the simple linear SVM. The main difference, or the hard SVM, sorry, the main difference is just that now we have slightly different constraints on this dual optimization problem. And where these constraints come from, they fall out of how things go in terms of optimizing this dual, and a few assumptions we have to make that are required for convex optimization, that are required to have this be the optimal solution of a convex optimization problem. So this is again a place where, for the sake of this lecture, what's really important is the fact that we can solve this version of SVM where we introduce this slack variable, where now we can misclassify some points and we're just paying a slight penalty. At the end of the day, it's very analogous to optimizing our original hard SVM. There's just a couple minor differences in the constraints we have to feed to our solver. And section 7.11 in the Bishop book will go over this in more detail than I have time to give you right now. And so I highly recommend going over this section. And again, I don't expect you to know anything from the appendix or to look at any of the references that are given there unless you're interested in it. But in section 7.11, it has what's on this slide, but again, with a bit more detail, a bit more background. So highly recommend that. Okay. So now getting a bit of intuition for what this actual soft SVM learns and what these different variables mean. So the soft SVM is going to give us a solution like the hard SVM. And again, remember that the thing we're learning in the end when we solve this dual is we're learning a bunch of these alpha i's. These alpha i's that tell us how much does each training point contribute to the decision boundary. We're still learning these things. We also have these epsilon I, these beta I terms that we're learning as well. So in terms of what do things look like in a final solution after we've solved this soft SVM, well, first off, we have points that are on the right side of the classification boundary and not within the margin. So these are points that we just classified correctly, just like with a hard SVM. And just like in a hard SVM, these points play no role in the decision boundary. They are not support vectors. So if we have a point that we're correctly classifying, then this point is going to have an alpha I equal to 0. We don't care about that point at all. Points that are on the margin, they're going to have an alpha I that's greater than 0. They actually matter for the decision boundary, but we're not misclassifying them. So they're going to have an epsilon I equal to 0. So again, these first two cases, points that are on the right side of the decision boundary, not on the margin, and points that are right on the margin on the right side of the decision boundary, is exactly the same as a hard SVM. And again, the important thing is that we're representing this decision boundary. Oh, it's not there. Oops. Don't take too long with my slides, but we're representing this decision boundary as a sum over all of our training points and then alpha I times these training points. So some points don't matter. Some points are on the decision boundary and matter a lot, just like in hard SVM. But now we have some points that are within the margin. So these points we're classifying correctly, but they're within the margin. So these are points where we actually have a non-zero for this slack variable. And in particular, our slack variable for these, so how much we're kind of wrong, is between 0 and 1. If we happen to have a point that was right on the decision boundary, this is never going to happen, but conceptually it could happen. This point, we would have a zeta I equal to 1, exactly 1 for this point, and then anything that's misclassified, that's on the wrong side of the decision boundary, is going to have the zeta I greater than 0. So at the end of the day, we're solving the same optimization problem. We've relaxed it a little bit. And now we still learn these support vectors, where support vectors are the points where alpha I is greater than 0. But we also have these misclassified points. We don't need to worry about them too much, but we just have these extra slack where we're saying, okay, some points are within the margin, some points are misclassified. These points still aren't support vectors. They're not relevant to the decision boundary, but our model has to accommodate them with these extra zeta I variables. And again, just like before, only training points, data points with alpha I greater than 0 are the ones that actually matter for the decision boundary. Yep. Yes, exactly. It's a good way of putting it, yes. Yes. So it tells us, yes, so that's pretty much the right way of thinking about it, because that tells you in some sense the scale of these slack variables is in terms of the margin width. It's a bit weird because you're also minimizing that margin, so it can be kind of hard in terms of the optimization. But at the end of the day, this also helps you set what this C value is. Because if you remember that we weren't just doing this optimization, apologies for my weirdly slow laptop, but we actually have this C term, which tells us how much we care about these slack variables compared to our margin. And what this basically says is that if C is 1, well then we're kind of okay with things being, off by one margin unit. But if we set C to 1,000, this means that going off by just 0.001 of a margin hurts us a lot. So when you're setting C, this is the right way to think about C, is it's, in some sense, how much do we want to trade off having a good margin versus having misclassified points? And the units in this space are kind of the margin width. It's a great question. Yeah. Yes, indeed. C also introduces a bias variance trade-off. That's a very great point. So C here is pretty much equivalent to setting the regularization term in other types of optimization. So if you remember when we were doing L2 or L1 regularized, we had the main objective, and then we had plus usually lambda times our regularization term. Things are a little bit different here because now C is kind of has the opposite meaning of lambda in some sense, because if we set C to 0, this means that, well, I guess no, in this case, setting C to 0 is going to mean that we're really going to overfit, because we're not going to satisfy we're going to be perfectly correct on the training set. If we're setting C really big, this means that we're allowing our model to misclassify lots of training points, and we're going to end up with, in some sense, a lower variance solution. It's a little bit different because of the fact that, in this case, there's also the fact that we need to satisfy our constraints. So if C is totally 0, and our data is not linearly separable, then we won't actually find a solution. So yes, C is very similar to something we can use to trade off the bias variance, with the caveat that it also changes how easy it is to solve our optimization problem. And in some cases, if we set C to, for example, 0, we might not be able to find a solution. That's a great point. Yeah. Yeah. Oh, no, it's a great question. Yeah, so I'm showing everything here in terms of the green points. So the question was, for those listening in recordings, what here we're looking at how we misclassify the green points, and we're saying that zeta is greater than 1 for ones that are on the wrong side. What about for the red points? Would that mean that zeta is less than -1? No, it's exactly the same. Zeta is just greater than 1. And again, the reason for this is part of this trick that we play, where we're always assuming that our class label in this binary case is 1 or -1. And so whenever we're thinking about things here in terms of the green, everything is positive. And then when we flip to the red side, there's a sign flip, but then we also have this sign flip because we're multiplying by, let me just bring it up, we're always multiplying here by yi. So basically, we're always, this zeta is telling us how much are we misclassifying, and it's always greater than 1 if we're misclassifying. No matter if that's misclassifying a positive as a negative or a negative as a positive. We always make these things equivalent by having this multiplication with our target variable. So if our classification prediction's negative and the goal was negative, we end up with a positive value, but if we're incorrect, this term's always negative. It's a great question. It's a little bit, it's playing around with just positive and negative signs, but yes, we set things up so it's totally kind of a mirror image, and we could make this exact same plot here, but looking at the red points. And all these numbers would be the same, just flipped. I guess down here first. Yes. In this example, yeah, and it's shifted a little bit, but yes, there is, oh yeah, no, there's just one technically right there. Yes, in this example, there's only one support vector. This is a great point. You don't necessarily need, so because the margin is always going to be, so the margin is the distance from the decision boundary to the nearest point. And there could just be, we could have support vectors all on the green side, 5 points that are right on the margin on the green side and none on the red. But we'd still have a margin specified on the red side because it's just going to be the same width as this. So the margin is not, the margin, if the margin is, this is M on the green side, the margin always has to be equal to that M on the red side. So you don't necessarily need support vectors on both sides. Having a support vector just on one side will specify the margin for the other side because it's going to have to be the exact same width. And it's a bit of a weird point of also, I guess, this idea of how we end up with lots of support vectors, because what are the odds of points all being exactly the same distance away from the decision boundary? Part of the way to wrap your head around how that happens is it's weird to think about when you're working with relatively low dimensional data, but we'll talk about a little bit later on of how we can kind of do these SVMs in extremely high dimensional feature spaces. And once we move to these really high dimensional feature spaces, you actually do end up having many support vectors, not just one or two. Yeah, I'll start right here. Yes. So the margin, the way to think about the margin is the distance from the decision boundary to the closest point to the decision boundary. And there might be more than one point that are exactly that closest distance away, but there has to be exactly at least one, because that's how it's defined. Great question. Yeah. For points in the margin, those points are also going to have alpha equal to 0. They're points we're misclassifying, so they're not support vectors. And they have a non-zero, or they have, between 0 and 1 for zeta, and an alpha equal to 0? Great question, though. Yep, at the top. This is a great question, and in a hard SVM, in a soft SVM, that is not true. In a hard SVM, I believe it is not true as well. That is something that's an interesting question that I will actually think about and get back to you. And post in the discussion board, I'll try to remember to make an announcement. Great question, though. Yeah. There's a great, yeah. So the question here, if I heard it correctly, was say we run our SVM and we get a small or a big margin. Does that tell us anything about how well our model's doing? So it does, but it's all conflated with this C term, right? Because I think all things equal, if we had the same, if we had kind of two data sets that were coming from the exact same type of features and everything, and we used the same C, so we had the same trade-off between misclassification and the margin, and we had a bigger margin for one of the data sets than the other, that would tell us that in some sense we're more confident in the predictions on the set with the bigger margin. But the tricky thing is that in general, you're not going to have perfectly, and if you had perfectly separable data, then again, the margin is going to tell you the bigger the margin, the more confident you are. But in reality, we always have this trade-off where we're paying some penalty for things we're misclassifying, and that penalty we're paying for misclassification interplays with the width of our margin, so it can be a little bit hard to interpret kind of the raw width of the margin as a notion of confidence when it's partially determined by your decision of how big or small you made C. So that's why I think, like I said, in a perfect world with the same C, with data sets coming from the same kind of world that had the same types of features and everything, the size of the margin, if it's bigger, you'd be more confident. But generally, it's a tough diagnostic, also because it depends on the nature of the features, etc. But there is actually some ways of trying to get... So SVMs don't have natural ways of interpreting kind of what is the probability coming from the output, but there's ways to do that based on distance to the margin and things like that. And so some of these more advanced topics we don't cover here, but will allow you to actually extrapolate from the outputs that we get in terms of the width of the margin, what are the support vectors, and so on, to notions of confidence on different data points. So it's there's not trivial, and there is a relationship there, but there's no kind of easy way to just say, oh, bigger M doing better. Yeah. Okay, cool. So that is the soft SVM. This is a model that was, in some sense, the model that reigned supreme for machine learning in, I don't know, maybe the 90s. And why is it a nice model that people liked a lot? Well, I think there is this elegance to it where it has this nice way of looking at classification in terms of how can we set a decision boundary in such a way that that is kind of the best possible decision boundary we could make. That's what motivated this hard version of the SVM, where we had this problem where when we're doing just straight up finding a linear decision boundary, there's multiple different possible boundaries we could do. And so SVMs ask the question of, well, there's an infinite number of decision boundaries that could separate our data. What's the best? And we set this notion of best based on this margin. And then we came from this really idealized world of what is the best decision boundary in a perfectly separable data set. And we relaxed things and made things actually work with this soft SVM and these slack variables. And at the end of the day, this was a technique that actually did and still does work extremely well. And there's a number of really interesting textbooks written on it. By Vapnik is the author of quite a few of these. And so despite the fact you won't see SVMs being used in many papers being published in the last year or two, it's an extremely important method and was one of those methods that had this elegance in a way where, despite the fact that a lot of these optimization kind of tricks and transformations can be a little bit, I don't know, overwhelming and boring at times, there really was a nice change from a lot of prior works where they really just said, well, why don't we try this kind of loss function or this kind of loss function? It really came at the classification problem from a nice, like, first principles perspective. And so it had this benefit and elegance, and also really was the state of the art for a lot of tasks for many years, kind of especially in the 90s and going into the early 2000s. So just kind of continuing on, in terms of SVMs, everything was binary so far. How do we deal with multiple classes? So there's two ways to do this. I mentioned one after lecture last time, and this is the first idea here, which is quite simple. Here, say we have k possible classes. Well, we can just learn k separate binary classifiers. So we just have k different classes, and for every one of our classes, we just do a one versus the rest, or one versus all, it's sometimes called. So we turn our k-way classification into k binary classifications. That's okay, it works. A downside of this is that we end up with a really imbalanced data set, because supposing that our k classes are relatively equally distributed, when we're doing one versus all, the one class is going to be way smaller than the rest or the all class. So it works. It's a very standard way to turn a binary classifier into a multi-class classifier, but it's maybe not the best thing to do. The other thing you can do is you can derive a multi-class SVM, and here the trick you use is you define the margin as being the gap between the correct class and the nearest other class. So whereas in the first one we were saying kind of one versus the rest, the second one we're still doing this idea, but we're just playing this trick where we're just saying that the margin is the distance between this point and the nearest other, the correct class and the nearest other class. The math goes through pretty similar to what we talked about throughout this lecture. So these are two different options. Generally the latter is probably preferred, but people use both. Yep. Yeah, it's a great point. So they are very, very conceptually similar. There's slight differences in terms of the actual solution you come to in the optimization. So they're coming from the exact same kind of motivation. There's just differences in terms of how things are going to work. In the hard SVM, they'd be the same. The soft SVM, there's some differences in the optimization. It's a great point. Okay, so now we're going to quickly, and maybe not cover entirely this class, but we can run things over in the next class if we have to, but move on to the second way we're generalizing these hard SVMs from last lecture. So the first thing we did, which is in some sense the most important thing, is we made our model actually feasible by saying, okay, we don't have to have perfectly separable data. We just have to have data that's pretty separable, and we have some tolerance for making mistakes. Now the second thing we're going to do is we're going to actually allow us to have nonlinear decision boundaries. So far, we went from a hard SVM to a soft SVM, but it's still a soft linear SVM. It's still a linear decision boundary. And what we're going to do here is something relatively simple, which is that we're actually just going to replace our replace our x vectors, our input features, with some transformation of these input features. This is exactly what we did to make linear regression have more complicated decisions, and how we made logistic regression and all these different methods. Instead of just working with our inputs x, we're going to work with, say, x and x squared and x cubed, and different transformations of these variables. So we're taking x and we're transforming x by some function phi of x. And at the end of the day, we're going to have this same optimization problem. The only thing we've done here is, whereas previously we had x's, now we have phi of x's. So we're just applying some function to x. And again, this function could just be a function that takes our x and takes some polynomial expansions of x. So we have x, then we generate x and x squared and x cubed, or e to the power of x, or log of x, what have you. So it's exactly what we did before. We're just doing some feature transformations of our variables. And at the end of the day, same solution, but instead of taking the product of xi and x, we're taking the product of phi of xi and phi of x. So again, once we've trained our model, once we've learned our SVM, implicitly our weight vector is represented by some linear combination of our support vectors. Again, these alpha I terms are only going to be non-zero for the support vectors. So we still have this, and we still have the fact that our decision function, our boundary, can be specified exactly in terms of these support vectors and the features on these support vectors. Again, exactly like we had before, but now instead of x's, we have the phi of x's. And the important thing to note here is that to solve the entire SVM problem, to represent the decision boundary, and actually even to do the entire optimization problem, really we don't need access to the x's. All we ever are doing with the x's is computing dot products of x's and other x's. If you go back through the math, you'll see there's a way to represent the reason why we went through all this Lagrangians and duals and primals is that at the end of the day we came with a representation of the SVM learning problem and the SVM decision boundary, where we're representing everything in terms of the support vectors, but not only that, everything is really in terms of dot products of our inputs. And now we're just taking dot products of some transformations of our inputs. And in fact, what we can do here is that we can, instead of explicitly computing some transformation of our inputs and taking dot products, instead we can just assume that we have some function, and we call this a kernel function, where this kernel function is some function that takes two of our points and outputs the dot product of these 2 points after some feature expansion. So one way to think about this kernel is kind of like a similarity function, but it's a similarity function that is specific to some feature space. So if we didn't have any feature transformations, our kernel would just be the dot product between x1 and x2. But we can define all kinds of different kernels, where these kernels correspond to taking dot products in some feature space. So the other important thing here, and there's actually theoretical results that guarantee this is true, is that any time we choose some feature mapping, so we have some, we're going to take our inputs, we're going to take their squares and their logs and their so on, we're going to make new x's from our original x's. Anytime we do that, we're actually implicitly defining some kernel. So there's always going to be some dot product in this new feature space. So there's always some kernel function that specifies what the dot product would be in this higher dimensional feature space. And it's worth noting here again that the relationship between dot products and cosine similarities, so dot products are related to the cosine between two different data points. So again, dot products we can think about as being like a similarity. 2 points that have really high dot product are really close together. And so this kernel function is, in a sense, telling us some notion of similarity between data points. And so what is an example of a kernel function? Well, a relatively simple kernel function is just a kernel that corresponds to taking the quadratic term. So we take our original input features, and now we take the quadratic expansion of these. So we have x and then x squared. And what this works out as is that our kernel function is we're taking, in a sense, the dot product between these two things, and then we're raising this to the power of 2. And if we were to expand this out within this dot product here and take all these products, this is what we would get. And all we're doing here, again, is we're just basically taking this data point, taking the expansion to the quadratic terms, and then if we were to actually explicitly have this feature mapping, what it would look like is this, right? So we're including all of the quadratic terms. So for each one of our features, we have the square of that features. We also have the interactions between each of our features. Again, we're just taking our original x variables, and then we're taking the quadratic expansion of these. But the important thing to note is that we could take our feature vector and take all of these expansions, like we talked about in earlier lectures, where we said, oh, we can transform all of our features by taking squares and taking interaction terms. And then we could take the dot product in this higher dimensional space. That would work. That would be just fine. But, in fact, this kernel up here, just taking the dot product and then taking it to the square, that only takes time OM. All we're doing is a single dot product and then raising to the power of 2. This is going to give us the same answer as doing this explicit feature expansion and then taking the dot product of this higher dimensional feature vector, which takes time m squared. So what we're doing is that instead of expanding our input features in some interesting nonlinear way and taking dot products, all we need to do is use this kernel function, which gives us what the dot product would be in that higher dimensional space. And this only costs us a penalty or a runtime of OM, whereas actually doing things in this higher dimensional space would cost OM squared. And we can do this with more than just quadratic. We can do this with general polynomial kernels. So taking the dot product and raising to the power of d is going to give us something that's basically equivalent to taking the d-dimensional polynomial expansion of all of our input features and then taking dot products in that higher dimensional space. And by virtue of the multinomial theorem, if we were to actually explicitly compute the, say, the quartic expansion of our input features, that would cost a penalty that would require us computing m to the 4 different terms and then taking a dot product in that m to the 4 dimensional space. But instead, all we're doing is taking the dot product and raising to the power of 4. So again, this kernel function is giving us this value that says if we were to do this feature expansion and take a dot product in the higher dimensional space, what would be the dot product? But we can actually get that value without explicitly doing that feature transformation. And in general, this is really cool because what this means is that we can now have models where we can have extremely high-dimensional nonlinear feature spaces, but we never actually have to work in these feature spaces. As long as you have a kernel that corresponds to that high-dimensional feature space, as long as we can implicitly compute distances in that high-dimensional space without ever going there, then we can train an SVM. So this is something that's called the kernel trick. So this is possible because of the fact that we're working with the dual, because of the fact that we're not actually learning our W vector, we're actually just learning the weights on all these support vectors and taking dot products of input features and linear combinations of input features. We never actually have to learn our explicit parameter vector. We represent everything as just weights over our input features. We work in this dual space, and why we went through all of that work is because this allows us to use the kernel trick. This allows us to not actually have to take really complicated feature expansions of our data. It allows us to implicitly work with high-dimensional feature spaces just by defining clever kernels. And again, here, what we're saying is that this is our dual optimization problem. Previously, we had represented this as a dot product between xi and xj, and then the product between phi of xi and phi of xj. But now we replace all of that with just this kernel term. This is a term that takes these two and tells us how similar they are. And at the end of the day, to make our prediction, we're summing over all of our training points. I mean, really just summing over our support vectors, because we only care about ones where alpha I is greater than 0. We're summing over all of our support vectors and taking the kernel between the support vector and the point that we're trying to make the prediction on. And in general, these kernel functions can almost always be evaluated in time OM. To be a proper kernel, it should be possible. So what this means is that we could do SVMs in the space where we're taking, again, the quartic expansions or something crazy of our input features in a crazy nonlinear space. But we don't ever actually have to compute these nonlinear expansions. We do everything implicitly with this kernel. And so what are some other kernels? Again, we can use more types of polynomial expansions. It's pretty standard to add a 1 here, to add this little offset. A really interesting kernel here is what's called the radial basis or Gaussian kernel. So this is similar to things we've seen a lot in this course, where we're going to represent the similarity, again, the kernel between x and z as being e to the power of the negative of the distance between these things divided by 2 times sigma squared. So this looks, again, like a Gaussian distribution, sometimes called a radial basis, very similar to this weighing function, actually identical to this weighing function that we used in the nearest neighbor classifiers. But what's really interesting is actually if we do an SVM where we make the predictions with a Gaussian RBF kernel here and do all of our optimization with this Gaussian RBF kernel, that is actually equivalent to taking dot products in an infinite dimensional feature space. So we can't actually explicitly represent the feature space that we're learning in because it's infinite dimensional, but we can represent distances in that space via this kernel function. And that's all we need to do. So we can actually learn using this RBF kernel, learn in a space that's truly infinite dimensional, but all we ever have to do is evaluate something that costs O of m. So this Gaussian radial basis kernel is a very, very popular kernel because it actually corresponds to an infinite dimensional space. And you can do other things. This is called the sigmoidal kernel using the tan function. I'm just showing an example here. This is actually what the Gaussian kernel looks like, so it can learn these really nice nonlinear terms. And there's a reason why Gaussians keep coming up in this course. It's because it's a very, very nice function and is really critical in a lot of the underlying theory of machine learning. So the really key idea here is, again, we did all these optimization tricks to come to this dual version of our SVM. We're representing everything in terms of our support vectors and distances relative to our support vectors, and we did all that so at the end of the day we could apply this kernel trick. And really quickly, I should say that kernels go beyond SVMs. This kernel trick is somewhat ubiquitous throughout machine learning. You can do it all over the place. You also can come up with all kinds of interesting kernels even if your data is not simply just real valued features. So what's very cool about this now is that we don't need to specify features of our data. We just need to specify distance functions or similarity functions on our data. We've turned the feature engineering problem into a kernel engineering problem. So for example, for strings, you can think about having kernels based on edit distance, things like that. And in general, you can actually kernelize even things like logistic regression and other techniques. So now we have this interesting idea where we've again flipped the feature engineering problem on its head, where instead of designing good expansions, good transformations of our features, instead all we do is we figure out good kernel functions. And these kernel functions, when you start thinking about really interesting different types of data sets, like for DNA, all you need to do is, in a sense, define a good distance metric between 2 points or 2 different samples of DNA, and then you can learn an SVM on that data set. You don't actually need to ever compute features as long as you have some kernel, some distance or similarity function. And like I said, this dual formulation is really useful, very useful when you have sometimes a small number of data points and want to work implicitly in a really high dimensional feature space. Because again, now instead of having cost that's kind of large in M, the number of features you have, your cost is going to be more proportional to N, the number of data points you have, because you're working in the data point space, in the space of support vectors. So that's the trade-off here, is that, yeah, it's all well and good, but now we have to keep around the whole data set, basically, especially if you kernelize some of these other approaches. So that's all for today. Things you should know going from last lecture to this lecture is this perceptron, this simple idea of a linear decision boundary, how we introduced the idea of having a margin to make this unique decision boundary, the optimization, transformations, and tricks we used to transform this constrained optimization problem to get to this Lagrangian formulation, then the dual formulation, how we took this hard SVM, we made it soft, we made it nonlinear, and now this really important general concept of a kernel and the fact that instead of working with features, we can just implicitly work with features by working with distances instead. Yes, there is a way to represent certain forms of linear regression as just using dot products, and in fact, it's actually something that's stronger than regular linear regression, actually something called Gaussian process regression, and called Gaussian processes as well. We're actually not going to cover it in this course. It's a really powerful version of linear regression, but it's going to be covered in 652. So yes, it's not plain linear regression, it's actually something more. I think for the hard SVM, it must be the same.
Yeah, it would have to be because if you had something different, you would have tried that.
Yeah. Yeah. So I got confused because I was thinking about the perceptual